Hello, and welcome to this video on parallel computing. I'm here to provide you with valuable insights. The voice you're hearing is AI generated, and this video is supported by the Norwegian Research Infrastructure Service. NRIS is collaboration between Sigma 2 and the universities of Bergen, Oslo, Tromsø, and NTNU to provide national supercomputing and data storage services. These services are operated by NRIS and coordinated and managed by Sigma 2. In this video, we will perform matrix multiplication using Python and offer more details on executing Python production jobs on the Fram Linux cluster. After logging into Fram, we access the Login 3 node. For our production jobs using Python, we'll be using the work folder. I've created a folder named Python on Fram within the work directory. Inside the Python on Fram folder, we have 3 files with the same name but different extensions. First, let's examine the file with the F90 extension. This file contains the Fortran subroutine we discussed in video 36. Next, we'll look at the Python file, which is highlighted in green, indicating that it is executable. We're unsure if NumPy's matrix multiplication routine can use OpenMP for parallel computing. To test this, we'll start with a matrix size of 8192. In video 36, this calculation took about 32 seconds on a single CPU core. Now we'll execute it on 32 CPU cores. Let's examine the job script file with the sh extension. This script is similar to those we've used before with Fortran and MKL, and it requests 32 cores on a single node. We'll load the matplotlib module, which also loads NumPy and the Fortran to Python command. Although we're setting OpenMP environment variables, we're uncertain if they'll impact the NumPy matrix multiplication routine. The Fortran module is built using the same Fortran to Python command demonstrated in video 36. Finally, we'll execute the Python program and use script commands to measure the build and execution time. The remainder of the job script is unchanged, and we make copies of the files used for this job. Before submitting the job to the Slurm management system, we clear the terminal. Once submitted, the job is assigned a job ID number. Using the slurm queue command with the me option shows that the job has been running for 18 seconds. After the job completes, we notice new files in the folder. Let's examine the slurm output file. It indicates that the job failed, so there is something that did not work. We'll open the job script file to troubleshoot the issue. The only difference in the Fortran to Python command compared to what we used in video 36 is the application of the OpenMP option. We'll attempt to resolve the issue by enforcing the OpenMP option using the loading flag variable. Before resubmitting the job, we clear the terminal. After using the slurm batch command, the job is assigned a job ID number. Initially, the slurm queue command shows that the job is pending. Upon checking again, we see that the job has been computing for 11 seconds. Once the job is complete, we open the slurm output file using the correct job ID number. We observe that the matrix multiplication executed in less than 3 seconds, indicating successful parallel computing. This is a significant improvement compared to the 32 seconds required on a single CPU core, and the NumPy routines can therefore perform parallel computing with OpenMP. Let's clear the terminal again before examining the files created in the folder. We notice new files, including copies of the original files used in this computation, with the job ID number appended to their file names. Let's try a larger matrix dimension by opening the Python program. The matrix dimension is set to 32,768. In video 32, we concluded that this computation was completed in approximately 67 seconds using both the Fortran program and the Fortran MKL program. Before submitting the job, we'll make some changes to the job script with the Emacs editor. First, we'll update the names in the script to reflect the use of a 32,768 matrix dimension. We'll also skip the building process of the Fortran module, as it was already built for the 8192 dimension. Instead, we'll reuse the existing Fortran module by sending the updated matrix dimension to the initial Fortran module. This approach will provide a clearer indication of CPU efficiency during parallel computing. Before submitting the job with a matrix dimension of 32,768, we clear the terminal. After submission to the Slurm management system, the job is assigned a job ID number. Initially, the Slurm queue command with the me option shows the job is pending. After waiting for a while and checking again, we see the job has been active for 51 seconds. Once the job finishes, we examine the results in the output file using the correct job ID number. The matrix multiplication was completed in approximately 88 seconds, which is about 20 seconds slower than the Fortran program and the Fortran MKL program on the Fram Linux cluster. The job waited 59 seconds in the queue, and the CPU efficiency was around 86%. Memory usage was approximately 24 gigabytes, as expected for this matrix dimension. To use the scripts and files from these videos as templates for your work, you may copy them from the Saga Linux cluster. First, move to the folder Cluster Work Support Parallel Computing YouTube. Use the ls command to display its contents. You'll recognize many scripts and files from the videos, and you can copy any of these files to the home folder. In our next video, we will use a Python program that uses the Fortran MKL library on the Fram Linux cluster. I am looking forward to the next video, wishing you all happy computing in the meantime.